Hi again. We are back to focus our attention today on integrating powers of trigonometric functions. In this video, we will be looking at case 2, which investigates odd powers of sine. Now, why would we use odd powers of sine in particular? Of course, we would have verified beforehand that the integral is not basic, that previous methods, substitution and IBP, have failed, and that algebraic methods, including trigonometric identities, were unsuccessful in solving the integral. Odd powers of sine can be recognized with a sine function that is either alone or accompanied by a cosine, and the sine function has an odd degree. So how does this work? Well, we're going to use sine to the power 5 of x as a guiding example. In step 1, we're going to pull out one of the sine x terms and associate it to the dx. We hope for this to eventually be a du. In our example, that means leaving sine to the power 4 behind, and sine of x is joined to the dx. In step 2, we're going to use the identity cos squared of x plus sine squared of x equals 1 to replace all remaining sine squares into 1 minus cos squared. In our example, sine to the 4x contains a product of two sine square x's, and it is each of these sine square x's that will be replaced by 1 minus cos squared. In step 3, we will apply the substitution u equals cos of x with du equaling minus sine of x dx. Recall that we've placed a sine of x dx aside for that purpose of becoming a du eventually. Now, our integral was set up for the substitution except for the missing negative sign. I've incorporated a negative sign with the sine of x and compensated for it on the outside. All our terms are now accounted for and can be replaced by expressions of u. In step 4, you can complete the antiderivative process by using expansion, by splitting the denominator if necessary, and then we will return to variable x. Here's where we stood in our example. We have on the right-hand side powers of u, which we can expand, and then the power rule can be applied to each of its terms. A plus k is added as usual for generality. And finally, every u stood for cos of x and can be replaced. In the final step, I've also distributed the negative sign in front of the parentheses to the different terms. If the integral has bounds, then these bounds can be adapted as you apply the substitution. For example, here is an odd power of sine situation with fixed bounds 0 to pi over 2. We're going to follow our procedure as we did in our previous example. Our first step is to move a sine of x aside along with the dx. In step 2, all remaining sine square of x have to be replaced by 1 minus cos squared of x. Notice how, at this stage, the derivative of cos can be recognized as being minus sine of x dx, which is waiting on the right-hand side to be a du. So we will apply u equals cos of x as our substitution, with du equal minus sine of x dx. As we do this substitution, we'll change the bounds. The lower bound, x equals 0, means that u is cos of 0 and equal to 1. The upper bound, x equals pi over 2, means that u is cos of pi over 2, whose value is 0. Here is our new integral with compensating signs. The lower bound became 1, the upper bound became 0. If you do not like the order in which the bounds were appearing, you are allowed to switch them as long as you change the sign of the integral. At step 4, we can then use expansion in order to integrate the individual terms. In this case, a power rule applies to each of the terms, and bounds of u can be directly replaced into the function of u we have obtained as an antiderivative. Celebration is in order.